In this presentation, we'll discuss how big data issues have been tackled historically, and we'll look at some of the shortcomings of those solutions. At the dawn of large-scale computing, big data was dominated by specialized hardware and software vendors. If the computers don't give it away, the clothes and the hairstyle should fill you in that this picture was taken from the 1970s. This dapper gentleman here in the middle is working on a Cray supercomputer at NCAR, the National Center for Atmospheric Research, just down the road from my home here in Boulder, Colorado. NCAR was actually one of Cray's very first customers. Cray, IBM, and other large vendors had a near monopoly on big data processing in the 1970s and early 80s. The systems were incredibly expensive and complicated by 1970 standards, and both of those factors pretty much limited their use to large enterprise or government organizations. They each used very specialized hardware and software. You couldn't, for instance, take memory out of a Cray and put it in an IBM, and each system had their own proprietary software language and programming methodologies. Developers would have to relearn new languages and ways of working when moving between the platforms. Most folks specialized in one platform and never hopped around. These systems were also built on the premise of limited vertical scaling. You may, for example, buy your Cray with 50% of its memory, CPU, and/or disk populated, and then allow for additional growth later, scaling the server up or vertically. However, once you'd put in all of the hardware that the machine could accommodate, you couldn't simply add a second machine and then balance a load across the two. With the incredible hardware advances of the day, this meant that organizations like NCAR, who needed to keep growing their analysis capabilities, were slaves to the individual vendors' rollout and upgrade schedules. It was not uncommon for an organization to have to buy a new system every 24 to 48 months, as many of us do with our computers still to this day. With the cost of these machines being in the $3 to $5 million range in 1970s dollars, this meant that these machines were costing these organizations a lot of money. I know for a fact that NCAR still has one of these machines on display in their museum, actually hidden in the corner of the basement of the museum, not even warranting display on the main floor. The machine, just state-of-the-art 30 years ago, is now an expensive bench. Those trapezoid-looking boxes at its bottom are actually cushions for seats. This picture next to the machine tells an interesting tale of how many dozens of people it took to move, install, set up, and maintain the system. The part I find most interesting, however, is this bit here at the bottom, where we learn that the now years-old iPhone 3G almost has 8 times the compute power, 30 times the memory, 3 times the storage, and so on. Many, if not most of you, are now carrying around a supercomputer with double or triple that capacity in your back pocket. Because of the frustration around using specialized vertically scaled hardware, systems designed in the late 80s and 1990s began leveraging horizontally distributed processing. The example I always like to show here is the SETI at Home project. SETI stands for the Search for Extraterrestrial Intelligence. From years and years of capturing radio signals from various parts of space via a globally distributed radio telescope array like the one pictured here, SETI found themselves sitting on mountains and mountains of big data. What SETI wanted to do with that data was to process it looking for patterns of something besides random noise, patterns which may indicate that we're not alone in the universe. SETI took a look around and realized something interesting had happened that they could use to their benefit. Many people now had internet-connected PCs, which they left on with just a screensaver bouncing around on the screen. The SETI at Home project, which still continues to this day, allowed users to download a little software agent to their computer. When the agent realized that the user was away and there was a lot of CPU and RAM available, it started calling out to SETI's main radio telescope database, pulling little bits of that data down, analyzing it, and then sending back a message to SETI that the data had something of interest or not. This was incredibly innovative at the time. It took the most time-consuming part of the operation, the processing, and moved it out to a horizontally scalable architecture. The processing of a set of data might have taken 5 to 7 minutes, while the actual data read, write, and transfer may have only taken 30 seconds or so. The processing was the largest part of the overall analysis, and that's what they were able to distribute out. Horizontal scaling means we can simply keep adding more hardware nodes, and unlike vertical scaling, it means we have really no upper limit on the size we can grow our platform to. Horizontal scaling is a design paradigm we still see in place today with cloud computing. Although SETI hasn't yet found definitive proof of aliens, they do now have a couple promising areas of space, in large part due to their ability to scale out this processing to hundreds of thousands of individual computers. In the late 90s and early 2000s, many companies began replicating horizontally scaled systems like the one SETI was using. We frequently saw systems like this with the central data store providing the storage and many processing nodes providing the CPU and RAM out on the edge. When you come back to look at Hadoop, remember this central data store we have here. Hadoop now actually pushes that data storage back out to the edge nodes as well. Although the concept behind distributed computing is very simple, doing it is really tough. We have temporal dependencies, such as things having to happen in a certain order. We have to deal with nodes failing and recovering. And we have to make sure that every chunk of our data is processed once and only once. Early systems like the IBMs and Crays could not do this. It turned out that 90 to 95% of the time spent in data analysis was building these distributed computing engines, and organizations were only spending 5 to 10% of their time solving the business problem. This became a huge distraction for many companies. The last decade or so has seen a lot of interesting changes that drove many of the decisions behind systems like Hadoop. Commodity hardware is all over the place. The margins on this hardware is small, as opposed to the Crays and IBMs, who maybe had 100 to 1,000% margins. Vendors today might eke out 3 to 7% margins, and the piece parts are interchangeable. We could switch vendors in the middle of a rollout. We also now have commonly used languages like Java that many developers know and understand well. Moore's Law has continued running since the 1970s. Just about every 12 to 18 months, our cost of RAM and CPU essentially halves itself. And as we saw with that Cray poster board, our own cell phones are now way more powerful than multi-million-dollar state-of-the-art supercomputers just 2 generations back. Moore's Law has us in a situation now where CPU and RAM are no longer the bottleneck. With SETI, it may have only taken a bit of the time to copy the data across the network. Most of our time was spent on analysis. We've now flipped that. Network copy and disk read-write speeds are where the bottleneck occurs in most systems these days. Even many small businesses now find themselves in SETI's original position, sitting on mountains of digital data that they know has possibly real and profound value for their organizations. Lots and lots of companies from large to small want to do analysis on things like web server logs, point-of-sale systems, ad-serving systems, and so on. As more and more businesses go online or begin serving mobile customers, they find themselves kicking off even more of this potentially valuable data. In the last 10 years, storage has also gotten incredibly cheap, meaning that more and more companies are now able to keep a lot of the data they would have been forced to throw out just a few years back. In this video, we've looked at the historical approaches to big data problems and discussed several interesting technology and business changes in the last decade, changes that heavily influenced the design of Hadoop.